Hey, what's up, guys? Okay, so in this video that I'm gonna to introduce the very simple theorem, but it's very interesting called Chinese Remainder Theorem. And if you like this kind of video, please subscribe to my channel. Okay, so before we dive into the Chinese Remainder Theorem, let me just this is a simple number theory results, but let me just tell you the spoiler. So the spoiler is that basically after this video that we will show the proof idea is actually the same as Lagrange multiply. Okay. Okay. So before we start to prove and statement and state these results, let me just give you a simple question. So one simple question is that suppose I want to solve x equals to 8 mod 3. So let's say I know x is equals to a mod 3 and then x equals to b mod 5 and also x equals to c mod 7. Let's say this is the equation I want to solve x. Basically, I want to combine these three equations into one. Okay, so I should write if only if. And let me just tell you the answer. So let's say x is 78 plus 21b plus 15c. And modulo the 100, 0, and 5. Okay, and trivial exercise, right? So this equation I can write as so this is so if I divide it by 3, right? Then this is divisible by 3, and then this is also divisible by 3. And the 70 I can write 61 plus 1, 8. So actually this is mod 3. So this is 8 mod 3. Also, if we modulo 5, then 70 is divisible by 5, and 15 is divisible by 5. So the rest would be 5. So I can write it 5 times 4 plus 1. So actually it's b modulo 5. And if we divide by 7, then this is 70 is divided by 7, 21 is divided by 7, and this 15 is 7 plus 2 times 2 plus 1. So actually it's C mod 7. So now we prove that for any left equation, left hand side, or for any right hand side, we always satisfy the left hand side. Okay, so this is simple. This is a simple example, but so now I'm gonna to tell you that why this is true in general. Okay, so this is the Chinese remainder theorem. So let me just write down theorem. So x is bj modulo mj. Let's say j is from 1, 2 up to n. And then we need to assume that, so assumption is that any 2 of mi and nj has no prime factor, has coprime to each other, or any I different from j. Then there's a unique solution. Not unique, there's a solution X exist. exist. Okay. And can be written as B1 M1, B2 capital N2, up to Bn capital Nn. And modulo the product of M. Okay. So let's write down a proof. So basically, first is the first non-trivial proof is that as long as there are each two of them are coprime to each other, then there's a solution. And to prove it, we can imagine that let's say I write this x this, and so we suppose I want x satisfy this equation, right? Then I would make some condition on the capital M1 and also M2 and Mn. So let's solve it. So let's say this is true. I write x. let's say Ix modulo M1. And I hope that these all the M2 and Nn are divisible by M1, right? So, and M1 is modulo, and the capital M1 should be 1, modulo M1. So that X modulo small m1, lower m1 will be b1. So if this is 1, then I hope capital M1 is 1 modulo M1. And also M2 is 0 modulo M1. Up to Nn is 0 modulo Mn. And similarly, let me just write down, right? Similarly, if I working on a small M2, then I would say that, oh, M1 should be 0 modulo M2. And the M2 should be 1 modulo small n2, and the capital Nn should still be 0 modulo Mn. Okay. And similarly, that if I do the small m3, then M1, capital M1 should be 0, capital M2 should be 0, and capital M3 should be 1, up to Nn. And then this is modulo M1, M2, Mn. And you just keep going. Okay, so combine everything. What we have shown is that if M1 is, so M1 will be 1, M1 modulo M1, but 0 modulo M2, and also 0 modulo M3, and now also 0 modulo Mn. And similarly for capital M2 and for capital N2 and capital M3 up to capital Nn. Okay, so finally, if I can find a set of all this, satisfy all these equation, then by definition, our X will satisfy the previous equation, which finished the proof. Okay, and so now the question is that why there's a equation for M1? Okay, and this is simple, right? Because the GCD of the M1 and the M2 up to Nn is 1. So by the Euclidean algorithm, I can find x times, let's say x bar m1 plus y bar m2 up to nn, which is 1. So I can just that capital M1 to be, let's say, y bar m2 up to nn times nn. So since this capital M1 will satisfy all the rest of equation because it's divisible by M2 and M3 up to nn. So all these are true. So the remaining is to show that this capital M1 is divisible by small m1. And but this is trivial, right? Because this equation already tell me that if I divide m1 both sides, then I get then this term is 0. So I get y bar times dot is 1 modulo m1. But this guy is actually capital M1. Okay, so finish the proof. Okay, so yeah, so this is the basically proof of Chinese remainder theorem. So basically, so we construct the solution using this kind of way, and obvious, so we show that there is a solution. Okay. So let me just and actually infinite solution by modulo this. Okay. So let me just go back and solve this question. A357. Okay. So let's say we do this simple example. So example is 3, 5, 7. So the first one is that we need to find the 3x bar plus 25y bar is 1. And the answer is that let's say this is 2. And so it's 70, right? So 70, so I can write as minus 23. But it doesn't important. So this 70 will be the capital M1. Now let's solving the M2, right? So M2 is 5. So I need to find the 5x bar plus 21y bar equals to 1. So right, so this is let's see. So 1 is not good. 5 is let's see. So the answer should be is 3, right? So 14. So it's like 70 minus 6. Sorry, I'm stupid. This is incorrect. What else is 1 and minus 4, right? So minus 20 plus 21, right? So M2 can be choose to be 21. So let's solve M3. So M3 is this guy. So I want to solve 7x bar plus 15y bar, which is 1. And I believe this is simple. I can choose. Oh, okay, I cannot. Okay. Right, so this is I can choose this x to be -2 and the 15 to be y. So M3 should be 15. So the answer will be 70A plus 21B plus 15C modulo 3 times 5 times 7. So which finish the example. Okay, so this is the proof idea, and hopefully it's very simple that you can understand. And if we go back to see the proof construction, right? So basically, we are just solving each one. So each capital N1, N2, N3, and one by one. This is exactly the Lagrangian multiplier when you try to do the interpolation with different polynomials. With a given the roots of given the number of polynomials and try to find a polynomial which extrapolate all the points you have. So actually, indeed, the this is basically the proof. And yeah, we'll see you guys next videos.